Hi students, today we are going to continue the chain problems. Previously we discussed one problem. There is a table and over the table there is a chain. Chain is arranged like this. We did a calculation for how much is a mass and what is the fraction of length that can be hanged. We got a value of mu by mu plus 1. This is the fraction of the length, that if the least total length is L. So this is the value for fraction of the length that can be hanged. Now in this question, now we are going to see, now the chain, there is no friction here, mu is equal to 0. Okay, now the chain started falling down along the table. So what will be the velocity when the entire chain becomes vertical? Now the chain is in this way, situation 1. Now the chain becomes completely vertical, like I have shown in the like I am drawing. So total length will be L now. So what is the force that is acting? Now just see this part, how much fraction of the length is hanging initially. If you carefully calculate, downward force is equal to only one force that is acting, gravitational force that is acting on the body. Mass hanging into G. Okay, how much mass is hanging? Total mass by total length into, say initially length is x, initially x naught, let's take, or instead of x and x naughts we'll consider it as L naught amount of L naught length is present. So initially m by L into L naught into G. How we got this? Mass hanging by total L naught is equal to total mass by total length. Mass hanging is equal to L naught by L into m. This is how we got mass of hanging. Okay, into G. If you see carefully, this mass is remaining constant. Yeah? So no, as the chain starts moving, mass starts increasing. Okay, now it starts increasing. Now what will be the value of the length, gravitational force now? So gravitational force, if it is a constant force, W is equal to mgh, we would have directly applied. In this case, its gravitational force is not constant. Gravitational force is varying. Let's take x length is present here. Then downward force is equal to it is equal to m over L into x into G. Okay, this is the downward force that is acting. Force where x is a length that is hanging. Okay, net work done due to the hanging force, F gravity into dx is equal to change in kinetic energy, half mv square. What is the force due to gravitational force? M by L into x into dx into G. What is x varying from where to where? Initial position is how much? L naught. Finally how much is the length? L. You understood why we are changing this m by L into x into G? Because gravitational force is not constant. Okay, now initially L naught to L, capital L, is equal to half total mass into velocity square. M gets cancelled because m is a constant. G by L into x square by 2, L naught to L is equal to v square by 2 gets cancelled, and it is equal to v is equal to G by, this is L, okay, G by L, L square minus L naught square whole root. Okay, this is the velocity of the chain when the entire mass comes down. Now let's do the same kind of problem for the hemispherical shape. Next example, say there is a hemispherical body, its radius is r, chain is hanging here, it's hanging here. When the entire chain comes down, what is the value of velocity, find the velocity of the chain. Okay, so this one we discussed already earlier, but if there is a friction involved it becomes difficult. If the friction is involved we should find mu n. As of now no need to discuss this much difficulty question, we just need to change the final energy. No, this problem is not under this control. Okay, anyhow we'll solve this, we'll wrote it. So when an entire mass comes down, the potential energy of this is at the half of its length mg L by 2. This I think I discussed this model. Okay, no need to solve this. Okay, now in the same question we are making it little complicated. There is a chain, okay, and it is at the verge, it is in equilibrium condition. Equilibrium condition is nothing but the downward force is equal to upward force, which is nothing but there is a friction here, mu, and now the chain is moved little bit. Okay, now the chain started moving in the downward direction. What will be the velocity of the chain when it comes to when it becomes vertical? In the previous case there was no friction, understand, now it has become vertical. What will be the velocity? Listen to this part, it is just like the blocks. Friction also, if you see, in the previous case gravitational force was varying, downward force is equal to how much? M by L into x into g, okay, where x is the length that is hanging. Now if you see on the wall there is a friction in the backward direction, friction is equal to mu n, normal is equal to mass, this is normal, the downward versus mass hanging, m by L into L minus x into g, understand. Now net force is equal to mu m by L into L minus x into g, okay, this is a minus, and downward force m by L x into g, initial into dx. Why dx? This is the net force, this is downward force minus frictional force, okay. If you subtract m by L into g we can take out as a common factor, and if you do the subtractions here, and x by x dx is equal to x square by 2, and minus of minus it becomes plus. Wait a minute, we will add first x and plus x, 2x and wait, x minus of minus plus mu x minus mu L into dx, integral from where to where, L0 to L. We bought everything in terms of it is equal to change in kinetic energy half mv square, m gets cancelled, and mu plus 1 into x dx is equal to x square by 2 minus mu L into x, limits are from L0 to L, g by L is equal to half v square. If you substitute the limits, mu plus 1 by 2 into L square minus L0 square plus minus mu L into L minus L0 into g by total length L is equal to half v square. Okay, if we substitute v is equal to, then the simplification v is equal to 2g over L into mu plus 1 by 2 L square minus L0 square minus mu L into L minus L0 whole root. This will be the velocity of the chain when it is released from the edge, if there is a friction is involved here. Thank you.